on the deep ocean resilience. And just by way of introduction, last week I was at the Ocean Scientists meeting in New Orleans along with a number of other people here. And the one talk that that really struck me, that has stayed with me, was a talk by Antje Boetius from Hamburg. And she gave a keynote plenary talk about, she's a deep sea ecologist, and she talked about an experiment where 26 years ago, her mentor, Hjalmar Thiel, at the very sort of dawn of the period when people were interested in deep sea mining and mining the nodules, he decided to set up a disturbance experiment to see how resilient the deep sea was to disturbance. And they used a very simple instrument, just basically a farmer's harrow. And basically they went to the abyssal plain. There were a lot of nodules off Peru, and they just dragged that harrow back and forth, towing it from the back of their ship, back and forth, and looked at the impact. 26 years later, Dr. Boetius returned with modern instrumentation, cameras, and so on. They took the cameras down, and the furrows made by that simple harrow looked pretty much as they had 26 years ago. And they sampled the communities there, including the microbial community. Now, microbes turn over on the order of hours to days. And what was remarkable, what stuck with me, was that the microbes in that field that had been harrowed back and forth were still completely different from the microbial community in the undisturbed areas. So this is 26 years later. So I think as we look at the deep sea, the key point is there's a lot of opportunities there, but it's a very different environment from the shallow water. It has very different characteristics of resilience. So that's what we're going to be talking about today. I'm going to talk about the deep sea science and solutions for a resilient ocean. Now, for a long time, the deep sea was basically out of sight and out of mind. And I have a quote here from Plato, who didn't really appreciate the oceans very much, and he thought of the bottom of the ocean as sand and measureless mud and tracts of slime. I think for a long time, this was in fact our view of the deep sea, of the abyssal plain, basically a plain like that. However, what we've come to realize, certainly since the 1970s, there's been discovery of one very new and different ecosystem after another in the deep sea. And we realize now that the deep sea is a source of some of the greatest species and ecological diversity on the planet. It's a source of great scientific wonder. It's still very poorly explored, and there's a great need for improved stewardship based on scientific understanding and appreciation of its value. Now, what I want to point out in this talk, what I emphasize in this talk, is that there's opportunity and risk in the deep sea. Now, in terms of opportunity, the deep sea is really the last frontier on the planet. There are huge hydrocarbon energy resources in the deep sea. This is the Gulf of Maine. You can see how these are the oil exploration, oil drilling, how it's gradually moved into deeper and deeper water. It's now well over into 500 or 1,000 meters. And obviously, there's obvious risk. Here is the Deepwater Horizon oil spill. There's also great opportunity in terms of, there's huge mineral resources, not only the nodules on the abyssal plain, but there's also sulfides full of very valuable minerals on hydrothermal vents, and there's also cobalt crusts on seamounts. And there's also major fish resources, and this is an orange roughy trawl coming up with a huge trawl of basically orange roughy from the seamount in the Southwest Pacific. Now, one thing that, speaking here in Washington, is important to point out is the U.S. is probably the only major nation not to have signed on to the Law of the Sea Convention, and that really limits our ability to have a voice in the management and governance of the deep sea. So we don't have a voice in terms of the mineral management, and there is the potential for the U.S. to claim a number of additional areas around it for energy and minerals resources, and until it signs, it really isn't able to make those claims. Okay, so looking first at some of the risks, fishing and habitat destruction. One of the things that was noted with the development of deep water fisheries, they started in the Pacific in around the 60s with discovery of corals, and it seamount resources, fisheries resources in the North Pacific. And what's characteristic here is this boom and bust pattern. Within about 5 to 10 years, as each resource is discovered, it's basically largely fished out. And this is the Tasmanian orange ruffy fishery that I myself was involved with, and here's the orange ruffy. Now, why was there this boom and bust? One of the keys was the extreme life histories. This fish, which is only about this big, actually lives to be over 100 years old. And these corals are also living to be on the order of 100 to several hundred years old. So they have very low productivity and basically not very resilient to higher mortality rates. They're also, now this is a echogram showing the orange ruffy over a seamount. Many of these resources are aggregated over fixed topographic features like seamounts, so they're localized, and basically all localized spawning aggregations are very, very vulnerable to overfishing. And given their low productivity and their aggregation, the ability of fishing trawlers to basically find these, know where these features are, it's no wonder that these fisheries were fished out very quickly. After having been there for a while, we began to think about, well, what are the impacts of these fisheries on the seamounts? Now, when we started there were only 25 species reported from all the seamounts in the entire Southwest Pacific. We had no idea what was on the seamounts. This, in fact, was this is a photo from some of our work showing what an undisturbed seamount looks like. This is a seamount after it's been heavily trolled. Basically, there's about trawling on seamounts reduced coral cover by about 2 orders of magnitude. And a follow-up study showed that there was basically virtually no recovery after 10 years. In the North Atlantic, fishing isn't on seamounts, but there are huge reefs, cold water coral reefs. This is one of them called Ophelia, and this is a trawl that's got caught up on the corals and is left on the seafloor. So the caution really is that much of the deep sea exhibits extremely low resilience, and that's due to the very low productivity, extreme life histories, very low rates of recolonization, and basically the fact that these communities have evolved, that they're adapted to low rates of disturbance. Now, this has been recognized by the global community, and this is a figure showing the increase in number of countries that have set up restrictions to deep water trawling, and the millions of square kilometers that are now in reserves. Now, this actually looks a bit, as you can see, there's been a huge sea change in attitudes towards conservation. This looks a lot better than it actually is. A lot of these are paper parks, but certainly there is recognition. And this has been an ongoing issue in the UN General Assembly for about the past 10 years. And it is still ongoing. So I want to talk now about the deep ocean climate change, because I think this is really, in the long run, probably one of the greatest, most important issues for the deep sea. So the myth of is that the deep ocean is too remote, too well buffered from the atmosphere to be significantly affected by climate change. But the reality is what I'd like to show you is that the deep ocean is warming, it's acidifying, and it's losing oxygen. So this graph shows the ocean has absorbed about 93% of the heat and about a third of the CO2 emissions that have been taken up, and half of that is basically since about 1997. So the rate of uptake, as you can see, this is the surface ocean, and the deep ocean down here, the entire ocean is being affected, and it's an accelerating process. Now, ocean acidification is a key issue. Acidification and hypoxia are closely linked. So basically, this is showing areas of low oxygen and of low acidity. As you can see, it's concentrated in the Pacific, particularly the North Pacific. It's the areas of the Atlantic and the Southern Ocean are particularly good, just because of the deep convection there. So that essentially the areas of the ocean that where there's poor ventilation and old water and hyperactivity, such as the Pacific and the North Pacific in particular, are the areas with the most acidifying conditions. Recent work has shown that much of the North Pacific is already below the aragonite saturation horizon, so that aragonite will naturally dissolve in the deep ocean there. And we don't have proof of this, but there's an interesting coincidence between the distribution of deep water hard corals or Scleractinian corals and the acidity conditions. So these in blue, we see the instance of deep water coral communities, and you see that they're concentrated in the North Atlantic and in the Southwest Pacific, which are the areas of high oxygen and basically high pH. The areas of low pH, such as the North Pacific, have remarkably low instances of deep water corals, and even though there are many seamounts and suitable habitat there, and it seems it's been speculated that this is because the acidity there is already basically beyond their ability to survive. So as the deep ocean acidifies further, we can see that it's basically already at the limits of what it can withstand. Okay, declining oxygen is probably one of the greatest issues, though, for the deep ocean. So this is showing the deep ocean low oxygen areas in the tropics, and also in the North Pacific, areas of eastern boundary currents of hyperactivity, where basically there's poor ventilation, hyperactivity, and poor ventilation. What's remarkable, what's concerning, is that time series throughout the North Pacific are showing declining oxygen. So these are from all around the North Pacific, from the Gulf of Alaska, British Columbia, Oregon, and Gulf of Southern California. You see for the last 20 years or so that oxygen has been declining. Apparent oxygen utilization has been increasing, particularly in the tropical areas and the North Pacific, and oxygen levels have been declining in all those areas. So this is a global issue. It's probably linked to climate change. And the reason, basically 10 Earth system models all project widespread oxygen decline at intermediate depths. Why is this? Well, first of all, warm water holds less oxygen, but probably more important than that, a warmer ocean is a more stratified ocean. So there's intensified thermal stratification. Also at high latitudes, there's anticipated to be stronger precipitation, so there's more freshening. So this leads to a reduced exchange between the mixed layer and the ocean interior. So what are the impacts? At Cal Coffee, which I was directing, it's probably one of the world's foremost ocean observation programs. We sampled this area of Southern California. At each station, we take not only hydrographic measurements of temperature, salinity, and so on, but we take a plankton tow to 200 meters. Now, it turns out that, okay, all the fish eggs and larvae are taken out and identified to the lowest possible taxon and enumerated. Now, it turns out that not only the near surface fishes, but all midwater fishes have their eggs and larvae up in the upper water column, and the abundance of larvae, because they're caught at very early stages in their life history, is a very good proxy for spawning stock biomass. Now, what we see here, okay, so there's several hundred taxa that we have identified from this region. I undertook a multivariate community analysis to see what are the dominant patterns. It was expected that the dominant pattern would have to do with the changes in sardine and anchovy, which has been the major focus of research. But in fact, the dominant pattern, the first principal component, had to do with the changes in 24 taxa of midwater fishes. So these included plankton feeders, predators, vertical migrators, and non-migrators from some 8 families. Basically, there's been a 63% decline in midwater fish abundance for these 24 taxa. Basically, it's very highly correlated with changes in midwater oxygen. That's in green. The first principal component is in blue. Basically, as oxygen has declined, the abundance of these has declined. The abundance of midwater fishes has declined by about 63%. This has also led to a decline in species richness or diversity, because the midwater fish community is probably one of the most diverse communities among the most diverse fish communities. What do we care? Why do we care? Well, it turns out mesopelagic fishes are the most abundant and most largest biomass of fish in the world's oceans. There's estimated to be about 10 billion tons of midwater fish in the world's oceans. That compares to, say, about less than 100 million tons of commercial fish catch. So it's about 100 times higher abundance of midwater fishes. These are the dominant conduits between the secondary productivity, the plankton production, and the higher predators throughout the world's oceans. So many marine mammals, seabirds, squids and fishes, predatory fishes, basically they're all feeding on these midwater fishes. Now the concern is, the big question is really, is this a local phenomenon that we're just seeing off Southern California, or is this on a larger scale? Well, without time series, we really can't tell. But what I'm proposing is that we need a global network of these of ecological time series based on local fishes, which sample the whole entire large part of the fish community. It turns out that we actually are a large way towards that. So all the major NOAA centers carry out these time series. Canada and Mexico have them as well. And NOAA has agreed to sponsor 2 workshops this year, basically to assemble these time series, which are available from around the continental US. They're also available elsewhere in the world, from Peru, Taiwan, Australia. And basically to bring these time series together and to be able to analyze them, to assess the magnitude and coherence of change, and basically to develop ecological indicators which can be used for ecosystem-based management and used for ecological assessments. So I'm hoping that I've convinced you that the deep sea is no longer out of sight and out of mind. There's really incredible diversity in the deep sea, and but it also has great resources, but it also has very special issues in terms of resilience. And what's needed is really development of time series and an appreciation of its unique characteristics for management in the future. Thank you.